Hi and welcome. I'm Marco Schmid from Schmid Elektronik, and I want to show you today how we use telemetry in data-driven racing in motorsports. And now we dive into a very special community, I tell you. It's the Shell Eco Marathon. That includes 10,000 students coming from 800 universities from 50 countries. And they are visionaries. They kind of make room for innovation, make room for the new. They are very competent technicians that make sure everything works correctly. They are kind of the backbone of the event. And then there are our athletes. They are our heroes. It's the drivers, it's the teams. Everything is revolving around these guys on these events. So you see what kind of vehicle they are driving. We are talking about highest energy efficiency here. So on the top right, you will see what we call the prototypes. They're very sleek, high-tech, and they deliver the highest possible energy efficiency, while on the lower left you see more the practical approach, the urban concept class that is made for real-life applications, and then the drivers. And to give you an idea of the extraordinary results these guys achieve, imagine a distance from London to Rome and back. And boy, imagine they make that road with 1 liter of gasoline. That's impossible, isn't it? So that means if you compare that to your daily commute to and from work, you make the 20 kilometers with just 1 teaspoon of gasoline. And what I like most about this event, it includes internal combustion engine, hydrogen cars, as well as battery electric. So it's a combination of all the 3 energy types. My role here is twofold. First of all, in between the seasons, I give presentations like that, learning sessions. I promote the data telemetry off-track award, give webcasts, and when I'm at the event, I am the technical guy, squeezing into the engine compartments, get my hands dirty, prepare the telemetry system hardware, give instructions to the teams and help them, coach them how to use it. And that's my role. And all I can tell you is that sustaining energy and clean mobility is very close to my heart. And that's why I attend the Shell Eco Marathon as a volunteer since 2016. Yeah, and besides that, I'm the CEO of Schmid Elektronik, who happens to be a partner of Shell Eco Marathon. And this is the kind of the connection that we have with Altair. We both are Shell Eco Marathon partners. And what we deliver here is we deliver electronics that powers the telemetry system that includes prototypes, MVPs, and series products. And as you can see, we are also a partner of National Instruments, NI, that happens to be a global player in test and measurement. Yeah, what's all about data-driven racing is we really want to transform the races. We want to transform the drivers. We want to transform the teams. We envision a competition that kind of follows a data-driven approach, that digitalizes it. That we also imagine that we can innovate the driving strategy and the driving tactics. And overall, we are thinking about, thanks to data-driven approach, to increase on-track performance while at the same time increase the energy efficiency even more. And see, today we'll find out how far this goes. Underneath is a technology that we use in the Industrial Internet of Things. We look at the building blocks of the IIoT. It starts all with a digital twin, a cloud server that holds a digital twin that is asking now for data that it receives from a bunch of sensors that are out in the field, out on the edge. And then finally we visualize the data, we kind of process the data, and we even apply some data science on it to get predictive results. This is, I would say, the building blocks, the underneath scheme. And now we apply Internet of Things technology to telemetry in motorsports. So here the sensor is a car that sends data to its digital twin. We make a live visualization so we can see where the cars are on the track. We do some data processing to analyze the performance of the day. And then we do some data science to get some predictive results. And what we do now is we dive into every piece of that building block and see what happens there. Start with the cars that are connected. We have the energy source. We have the driver. Then we have an embedded systems that connects to internal sensors using a measurement network. We have a relay that with that we can stop propulsion at any time. We have a GPS receiver, and we have an IMU and many, many sensors more. But these are the essential ones. Now let's deep dive into the embedded system and what are the building blocks of the embedded system. So you can see there's a bunch of functionality that is on a very tiny board that connects the board to the internet, that connects to the internal sensors, has a lot of functions in it, is powered by a very strong microcontroller. And then this board again is installed in a small 3D printed housing that is put on top of the vehicle to get sensor data from there and connects this vehicle to the internet. Now let's have a look at this energy sensors. It starts with the liquid flow meter for internal combustion engine. So here we have the liquids going in and out, and we have a system in there that measures many thousands pulses per milliliter, makes it very accurate. And there's also temperature that we are going to measure in order to compensate for it. In order to make that smart, we bought a commercial sensor and put in a specialized version of an embedded system that kind of converts the physical value on-site and makes them digital and send them to the embedded system via CAN. That is pretty common in automotive industry. And what we receive from here is the used milliliters that are used while the engine is on the track. And here we see how it looks like in the compartment. We see how the fluids go through the sensors, and on the right hand side how is it connected to the embedded system through a CAN bus. Battery electric uses a Joule meter. We see here the two bars. They are connected to the battery terminals, so we measure the current going through these bars and the voltage that applies there. So from that we measure the power, and from there we get to the joules. And again, the same technology is used. We put in a smart board, an embedded system that makes the sensor smart. So in order that we convert the physical value on-site directly into digitalized value that are sent to the embedded system through CAN. And this is how it looks like. It is installed in the battery electric cars. And then we have the gas flow sensor used for hydrogen to see how many liters, normalized liters, the fuel cell is consuming. And this is again installed in the engine compartment and connected to the embedded system. And now we have 3 sensors depending on the energy type being used. Last but not least, GPS. At first it seems very easy, I would say easy sensor acquisition, GPS data. However, you need to know that in order to get proper GPS signals, you have to have a direct view to 7 satellites, and this is seldom happens on the track because sometimes we have high-story buildings beside the track. We have bridges crosses over the track that kind of leads to dropouts of the signal, or maybe deflects it and reflects it, and this leads to faulty signals. And there were some funny incidents on the track. So we have seen the vehicle was really on the track, while on the big board of the visualizations they were really moving in a nearby shopping mall. And I remember the headaches we had in Detroit, in the canyons of these high-story buildings. This was really a nightmare, and as you can see on the first measurement that we took before the race, there was really a high distortion on the GPS longitude and altitude, and there was a lot of work necessary and improvisation to make that work. So I would like to use GPS data now to show you the flow from the sensor and how this physical value makes it through the whole stack of software until it arrives at the cloud. So it all starts with a GPS signal that is picked up by a GPS sensor. There are a lot of commercial variants around there, for example from u-blox. And this GPS sensor translates the signal into the NMEA format, which is pretty tricky to read, but if you know the structure, you can immediately see the longitude and latitude there. And this is then kind of fed into a service that only picks the relevant information there and copies it into a new data format, a data format that is then sent to the main program that handles this information. and together with other information kind of can generate a data stream to be stored on a local CSV file. Or we translate it into JSON format. That is really common in this in applications like that. And through MQTT, we send it to a cloud. MQTT stands for Message Queuing Telemetry Transport, also pretty common in IoT technology. And so here we see the stack, how the sensor values makes it up to the cloud. And we not only have GPS, but we also have the Joule meter, the liquid flow meter, and the gas flow sensor. And all this data is then aggregated in a main program powered by the Linux operating system. The whole program written in C. And so this is now what we call the embedded software that runs on the embedded hardware. And together, it's this embedded system that produces the data points. And here it is installed on the car. A car that is moving around the track. So we receive now sensor data, send the sensor data to the cloud, and this is where we go next. So the cloud service is a digital twin. Starts with receiving data packages from our embedded system through an MQTT broker. A kinetic server picks up these data packages, smoothes it, validates them, massages the data, makes sure everything is good, everything is how we want it, then stores the data in a database for further usage. We also update the monitoring health system to see everything is going right on track, and then we push data to visualization services. We soon get into these ones. And the kinetic service is really, I would say, the heart of this cloud server. It uses an underlying node map that we always model when we go to a new racetrack. And as you can see, it's evenly divided with evenly divided distances. Also, the start-stop line is modeled here so that we can check, is a car on track, is it off track, how long does it is on the track, what's the distance traveled, and so forth. And then data is ready for visualizations. So first of all, we have what we call the Embedded Systems Manager. Here, every embedded system is connected to the manager. We can see if it's green, it's good to go. If it's yellow, we need to do something. If it's red, it needs immediate correction. And what's really great, you can really then zoom in and drill down and see what's happening on the component level. See, is it the temperature that's not going good? Is no fluid going through the liquid flow meter? So it's very easy to pinpoint the problems. We use it every day as a technicians. We walk around, we look into look into these telemetry systems. So we have literally their digital twin in our hands. Like on the left-hand side, these guys are now queuing up the start line, and we just make sure is that everything got a green light. And on the right-hand side, the guy will check the car first before it's allowed to go out on the track. And now they're out. We keep tablets in our hand, see that energy is now consumed. We look at the status signals. Is everything green? That's good to go. So we know that everything that the prospect is seeing on the big screen is running well. And this is what the prospect is watching. So we have the live leaderboard on the left-hand side. We have on the right-hand side this live map where we see exactly where the cars are, who's first, who's last, what lap they are, and what remaining energy they have. And it's really great. And finally, the last lap is the most exciting one. So there's tension, drama, while you see the cars moving towards the finishing line, and everybody's wondering who will be the winner of this competition. So much for live data. Now we look at the end of a race day. There's a lot of static data that we want to process and analyze to see what is going on. Do we have? Can we improve something? That means a lot of data is stored in a CSV file and in the database. And what we do now is read the files and pick out the exact data that we want. Something like Joule meter data that is sampled at 10 Hertz. So on the left-hand side we see the volts, the amps, and the power, while on the right-hand side we see the accumulated joules. So that means if the car goes out, while he's on the track, energy consumption goes up, and sometimes we see a peak like in there, and then we see maybe he has put too hard on the throttle, and that used more energy that anticipated. So this is the first easy to use analyze method. Liquid flow meter, gas flow sensor. Here we also measure the temperature, so that means if the car goes out to the track, the engine compartment gets hot, temperature rises, and then we need this temperature to kind of compensate in the smart sensor itself. On the right hand side you see the instantaneous flow on the lower part. So here we have, if you hit the throttle, you accelerate, then you use more energy, so you get these energy spikes, and this leads to this cumulated flow that you see in orange on top. And this orange line also shows these ripples, and these ripples are directly connected or linked to the spikes we have in the instantaneous flow. We also can plot the longitude and latitude, which, okay, doesn't make a lot of sense because we see here, you know, the trajectories. But what would make more sense is that when we would have the race line for each lap, and now we move into the data science to make that happen. So what we first do, we add the start line, stop line, and the lap line, and that allows us to split the trajectories onto the different laps. So every lap has now a different color, and this allows us now to estimate or to analyze the different lap and the race lines. So like on the left-hand side with internal combustion engine, you see the energy consumption per lap, so you can see on a lap-by-lap basis how you do, and on the right-hand side the battery electric. And this really helps to see what was your first best lap, what was your worst lap, and maybe what did you do in between, what was the driver doing different. And at the same time, it's still, I would say, challenging and tough to really understand what's going on the racetrack itself. And this brings us to these facet plots where we kind of lay out all different laps. So you can see at a glance what's happening, where you have the long burns, where you have the tight short burns, how you did corner 1 in lap 2 compared to lap 5, what did you do differently, and how this led finally to these differences in energy consumption, and to get to ideas to make your runs better. Brake-specific fuel consumption is another data science method in order to find the best target region to operate your vehicle. So we have the vehicle speed against the road load force, and this certain region where your driver would create the best results. You can use other commercially available tools such as NI-LabVIEW to analyze the data, to get out more meaningful information. There are the strong and very advanced Altair tools, like Panopticon, that allows to analyze the historical data and also live data. So, but what's important, what I wanted to show you today, how we can really leverage race data through telemetry, through this kind of generic tools building blocks to get what we want, to get the information that allows us to improve our results. So the presentation I gave here today, we also, as a data technology team, we provided one to the students earlier this year with the idea to kind of motivate them to use data to make their results better. And what we received was really astonishing. So we received about 50 submissions, and they were really inspiring and kind of fell into 3 categories. The first categories, they were creative. So they used really cheap and economic platforms to, at the same time, get some sensor data and send it to the cloud. And on the top right, you can see how they used analytics to compare the results to kind of estimate what energy efficiency they can achieve with a telemetry system. The second category used digital twins of the cars and of the racetrack. They kind of come together in the cloud in order to find the best racing strategy that is then downloaded into the cars. And the third category here, we felt like being in the Tony Stark's laboratory, where the driver is supported by high-tech assistance systems that shows him exactly which race line to follow in order to have the best possible race line. So that allowed him to completely focus on what's happening on the track, to overtaking and stuff. And that's really fantastic. And this kind of motivated us again to move down that path, to kind of follow this digital transformation of race teams and driver, and following the vision that we can, with the data, improve the strategy, improve the tactics, and that finally leads to a higher energy efficiency, while also maybe increase the track performance as well. Yeah, that was it from my side. I hope you enjoyed it. Thank you very much for coming. If there are questions afterwards, fire away. Otherwise, I thank you again and wish you a great and inspiring Congress and webinar. Bye-bye.